All right, so let's take a look at the second section of 6.3. We're going to learn the last two transformations that we haven't done yet. They're the stretches. They have special names, so we'll talk about that. It's basically a horizontal stretch and a vertical stretch. This is the last day we'll look at individual transformations. Tomorrow we'll look at putting multiple ones together and solving some equations, but we're going to do it on the calculator. So tomorrow we'll use calculators. All right, so first thing I'm going to talk about is what's called the amplitude. The amplitude of a sine or a cosine wave. Sine and cosine are the only two trig functions that have an amplitude. The reason the other trig functions don't, we'll see that on Thursday, but I might have shown you a picture yesterday. The other trig functions don't look like waves. So the amplitude basically measures the distance from the center line to the highest point, or from the center line to the lowest point. Same thing. So the amplitude is measuring a distance. If you measure a distance, what kind of number does that have to be? Positive. All right? Distances are never negative. So if you're ever looking at a graph, which you will be on the test, and I ask you, what is the amplitude of this picture? You would never give me a negative answer. Okay? It's always a positive number. And I think I say that later on, but just keep that in mind. Amplitude is always positive. So an amplitude change is basically what we call a vertical stretch. If you make the amplitude higher, it stretches. If you make the amplitude lower, it compresses. Whenever you add or subtract, that's a shift. Whenever you multiply, it's a stretch. The only question is, when you multiply, where did you multiply? Did you do it inside, right next to the x, or did you do it outside the function, out in front? If you do it out in front, that's an amplitude change. So you'll have a number in front of sine or cosine. So if I give you a problem, I think we're going to do a couple in a minute. Yeah, I'm going to give you some examples and we'll find the amplitude. That's how you find it. You take the absolute value of the number in front. Now, that number in front could be negative. Okay? And if it is negative, you have to take that negative into account when you draw the picture. But if someone's just saying, what's the amplitude? The negative doesn't matter, because the amplitude is like a height. Height's always positive. Does anybody remember what happens when you put a negative in front? What does that cause your graph to do? Yep. Flip. So the negative would cause a flip when you sketch it. But flipping doesn't change the amplitude. Okay? So you always take the absolute value if they ask, what is the amplitude? And that part I already said. You're stretching or compressing the graph along the y-axis. So just a quick example. Let's do sine x and 3 sine x. So it's an amplitude change because I put a number in front. What do you think the 3 is going to make it do? Is it going to stretch it or is it going to compress it? Yeah, it is going to stretch it. Okay, and if we look, speed it up a little bit. There's the original. And there's 3 sine x. Notice all the x-intercepts are exactly the same. Doesn't change the x-intercepts. Those are like glued in place. All it does is stretch it taller. All right, so let's find the amplitude of that one. 3 cosine x. Alec, what's the amplitude there?
3.
3, that's it. The amplitude is 3. How about in B? What's the amplitude there? Yeah?
4/3.
Yeah, it's 4/3. There's all kinds of other stuff happening. there's a phase shift, there's a vertical shift, but that has nothing to do with the amplitude. Just focus on the number that you're looking for, which is the one in front. All right. How about C, -2 sine x? What's the amplitude there? Jake?
-2.
2, yeah. Take the absolute value. What if I did this? What's the amplitude now?
2.
It's still 2. That negative doesn't cause any change in the amplitude. The negative would cause something like this to happen. If that's the original, that's what would happen if you put a negative in front. It flips it. But doesn't change the amplitude. Okay. So any questions on finding the amplitude? You probably have 2 questions just like that on the test. Find the amplitude. No sketch needed. All right, so let's take a look at what that would sound like. All right, so we heard the phase shift yesterday, kind of that weird effect. Some people said it sounded like it was moving. Some people got quieter in certain spots, it got louder. Kind of depends on where you sit. Everyone's going to hear the same thing with this one. Okay, doesn't matter where you're sitting. What do you think happens when you stretch it and make the wave taller? How do you think you would hear that? The pitch what?
It gets higher.
Okay, the pitch, wait, can you say that again?
The pitch gets higher.
Oh, the pitch gets higher, okay. So the pitch could get higher, or what else could change about the sound? Yeah?
The volume itself.
The volume could change. So let me change the amplitude, and you can see what happens. So there's a sound that's 1,000 hertz, and I'm going to make the wave taller, and you can see what happens. So what happened when it got taller?
Louder.
It got louder. If I drag it back to the left, it starts to get quieter. So stretching, louder, compressing makes it softer. And this program isn't perfect, but in theory, if you dragged it all the way to the left, that's 0 decibels. There should be no sound at that point, but it still kind of plays a little sound. What?
Can you play it?
I can. It's not really that interesting, but
I want to hear it.
yeah. It's still a very little sound. It should be off at this point, though. I gotta talk to the programmers. They gotta do a better job. Maybe I'll fix it. So that's amplitude change, all right? Changes the volume. So we're stretching and compressing it along the y-axis. So we got to figure out from that original table what's going to happen. So what values are going to change? You got all your original coordinates. Is it the x's that are going to change or the y's? Al?
Y value.
The y values are going to change, which means the x's stay the same. We like when the x's stay the same because the x's all have all the fractions with pi. For this transformation, we don't have to deal with them. Every amplitude change we do in this section, your x's are 0, pi over 2, pi, 3 pi over 2, 2 pi. They never change, as long as we're doing vertical stretches. When we do horizontal, that's different. So x's stay the same. The y's are going to change. Very simple arithmetic to find the new y values. Just take the old y values and multiply them by c. Notice it doesn't say absolute value of c. Okay? The only time you take the absolute value is when they ask what is the height of this graph, and you're just going to write a number for your answer. But if the number in front is negative, that negative makes a difference when you graph it. It flips it. So keep the negative. If it's positive, just keep it positive. Just whatever they give you, that's how you use it. And those are the 2 steps for vertical stretch, or amplitude change. Same thing. So actually, I think I did sine x and I did 3 sine x on the calculator, so you kind of know what it's going to look like. But sine and cosine are a little different. All right. So now we know 3 transformations. First thing I have to figure out, and what you're going to have to do on the test, is identify which one that is. Right? So we're studying a vertical stretch, so that's what it is. But how come? There's 2 things that make it a vertical stretch. One thing makes it vertical, one thing makes it a stretch. Yep.
There's a coefficient.
There's what?
There's a coefficient in
Okay. Can you be more specific?
like 3.
3? And what are we doing there? Like what operation?
Oh,
Multiplying. Multiplying makes it a stretch. And then the first thing she said is it's in front. Where it is makes a difference. If it's out in front, it's a stretch vertically. Okay? If it was inside, that would still be a stretch if it was multiplication, but that would be horizontally. So vertical stretch, x's stay the same. Isabel, what are my original x values? Whether we pick them from sine or cosine, they're the same.
0, pi over 2, pi, 3 pi over 2, and 2 pi.
Yep. So those are my original x's. And now my original y's, I'm going to put them off to the side. But that's just for my purpose to help figure out the new ones. So Nick, what are my original y values for cosine?
For cosine, it was 1, 0, -1, 0, 1.
Okay, now we take all those y values, and what are we going to do to them? Yeah.
Multiply by 3.
Multiply them by 3. So 3, 0, -3, 0, 3. That's it. That's all you have to do for a vertical stretch to get your table. Any question on the table? Okay. Now let's make our sketch. Okay, so there's my graph. I'm going to put 0 right on the x-axis. And I don't have a lot of space, so I'm going to scale it. And I'm going to make vertically each tick mark worth 3 units. For my x values, 0, pi over 2, pi, 3 pi over 2, and 2 pi. I don't have to change anything. Okay? So I'm going to keep those. I'm not skipping because I have 0 in the table. So, and they're all 90 apart. So we'll just go 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, and now graph your points. So we got 0, 3, pi over 2, 0, pi is -3, 3 pi over 2, you're back to 0, and then 2 pi back up at 3. And there's my graph. Now, when I look at that, it doesn't look bigger than any other graph I've been drawing all week. How come? How come it doesn't look 3 times as big on the screen? Because I scaled it. Right? I changed the scale of my axes. And that's how I do all of these problems. So if this said to graph 20 cosine x, I would have the exact same picture. The only thing that would be different is I would say that that's 20 and that's -20. I would just change the scale because I don't have enough space to do 20. So any question on that idea? So you're going to see a lot of things keep looking the same in this section, and that's because we're going to change the scale. All right. Okay, let's look at this one. 1/2 sine x. Emily's, what kind of transformation is that one?
Me.
Yeah, or you?
It's vertical.
Well, it's going to be some type of stretch, whether or compression. Yeah, it's going to change it vertically, right? So it's some type of vertical stretch or maybe compression. This one actually is going to get shorter. All right. So How about, Morgan, what values stay the same?
0,
And which column is that?
the X.
The x's. Can you tell me, go ahead, what are they? You said 0?
Pi squared.
Do you remember? Same ones we did on the last problem.
Oh, 0, 1/2, or pi, half pi, 3 pi squared, 2 pi.
I like the second one. That was good. 0, half pi, or pi over 2. Can someone remind me, what's the third one? Pi. And then 3 pi over 2. And then 2 pi. Yep. You don't have any exponents on pi all week, ever. So you'll never have like pi squared or pi cubed, just pi. Right? All right. Now the y values. Rebecca, what are my original y values for sine?
0, 1, 0, negative 1, 0.
Yep. 0, 1, 0, negative 1, 0. And Sam, what do I do to all of those?
Divide them by 2.
Yeah, divide by 2 or multiply by a half. It's the same thing. Can you tell me what you get if you do that?
0, 1/2, 0, negative 1/2, and 0.
Yep. So there's your vertical stretch. All right. So let's set up our scale. This time I would go by, I mean, you can go by ones if you want. If you want to go by halves, you can do that too. Just going to go by halves. And then the x values, label them just like we always do. 0, pi over 2, pi, 3 pi over 2, 2 pi, and plot your points. 0, 1/2, 0, negative a half, back to 0. Again, doesn't look like I stretched or compressed it at all. Looks the same size as everything else. That's because my graph paper stayed exactly the same. My scale changed. Any questions on that one? Okay. So just to kind of review, if I asked you, what's the amplitude of example 3? Okay, 1/2. What's the amplitude of example 2?
3.
3. What if I threw a negative in front? What would the amplitude be now? Still be 3. Okay. Let's actually look at one with a negative in it. What's the amplitude of that one? 1. There is no change in the amplitude. But this is not going to look like cosine. What's going to happen? It's going to be the cosine function, but it's going to upside down. It's going to flip. So we just did all the original y's and x's for cosine in example 2. So we've got 0, pi over 2, pi, 3 pi over 2, 2 pi. And now you're just going to take all the y values and make them the opposite. So you would normally have 1, 0, negative 1, 0, 1. Change the sign of every number. Negative 1, 0, 1, 0, negative 1. So normally cosine looks like a valley. It's like you're drawing the downward part. This is going to look more like an N shape, like a hill. Okay, it's the other part of the wave. All right, so we got 0, pi over 2 pi, and 2 pi. Right, so we're going to start at negative 1, 0, 1, 0, negative 1. And there's your graph. So technically there's no amplitude change there at all, but we put it in with these because it's kind of like you're multiplying by a number in front. It's kind of like having a negative 1 in front. Okay. Any question on that one? All right, so we've done the vertical shift, we did the phase shift, we've done the vertical stretch. The last one we have is a horizontal stretch. And a horizontal stretch is called a period change. So every single problem we've done up till now, the period has always been the same. Anyone remember in radians, how far do you have to go to do one full cycle? Yep. Pi. Every problem that's been trivial. That's the standard period we talked about yesterday. Well, now what we're going to do is we're going to stretch or compress it. So we're going to make the graph cycle faster or slower. When it cycles faster or slower, we have to figure out, well, how fast is it cycling? Is it twice as fast? Is it 3 times as fast? Like what's happening? So, period change is a horizontal stretch. Any kind of stretch always uses multiplication. What's the difference between the multiplication in this problem and the one we just did? Yep.
This one uses B instead of C.
Okay, yes, that is true. I used a different letter. How about, what else? Yep.
Its placement is different. It's inside the cosine function and not outside of it.
Yeah, it's in the function. It's inside the argument to the function. Anything that's inside the argument is always a horizontal. Anything outside is always a vertical. Multiplication is always a stretch. Addition or subtraction is always a shift. All right. So for our examples, we're only going to be looking at when b is greater than 0. Now, technically, it could be less than 0. And if it's negative, that would be a flip. It just would be a horizontal flip instead of a vertical flip. All right, so again, all our examples, b is going to be a positive number. There's no reason why it couldn't be negative, but we'll keep it positive. So period change is going to stretch or compress the graph on the x-axis. That means the x values are going to change. Those are the values we don't like to work with because they have pi in them. So you're going to have to work with the values that have pi. So let me type in an example in the calculator and let's see if you can figure out what's going to happen. Let me type in sine x and sine 3x. What do you think the 3 is going to do? Is it going to stretch the graph out 3 times as much or compress the graph 3 times as much?
Compress.
Compress? All right. Well, let's see what happens. So there's the original. Any reason why you guess compress?
I don't know. I mean, that's what it usually does.
So
Because it always does the opposite of what you expect on the inside.
on the inside, it's always the opposite. Yeah. You would think, well, if you put a big number, doesn't that make it bigger? No, not on the inside. A bigger number actually makes it smaller. And let's.
Because the ending result of inside will reach 90 degrees faster, etc., at least.
Yeah. So if you look at it carefully, I put in a 3. Look at just this section right there. Right? That's one cycle of the blue graph. It goes up, goes down, back up. How many times is the red graph going up, down, and back up in that box?
3 times.
3 times. So the red graph is cycling 3 times as fast as the blue graph. Right? So for every 1 cycle in blue, you're getting 3 in red. If I had put a 10 in front of the x instead of a 3, I would be getting 10 cycles in the red for every 1 in blue. Now if I change it and I do something like 0.5x, now what's going to happen is for every cycle in blue, you're only going to get half a cycle in red. Okay? So notice, here's a full cycle in blue. It's only halfway through the cycle in red. It's done like the upper part. It still has to do the lower part. Okay? So it's always the opposite of what you would expect inside. So greater than 1, it compresses. Less than 1, but it's still going to be more than 0. It's stretched. The further you are away from 1, the more pronounce the end result. Okay. If you put in a really big number, you're going to get a lot of compression. Like if you put in 100x, it's going to go up and down 100 times for every 1 second. Okay. So, stretching and compressing horizontally. What do you think that would do to the sound? The only thing the sound hasn't done yet. Yeah?
Change its speed.
What do you mean by speed?
Well, like, how? Explain it.
So the speed of sound, if we're talking about in air, is a function of the temperature. That's the speed. Like if I was a mile away and I yell something, how quickly you hear it, like if I could yell out enough, would be a function of how warm it is out. Basically, that's the speed. Sound travels very slowly in air. Like if you had, let's say you had a piece of metal 2 miles long, like a very long piece of metal, and you put your ear on that piece of metal, and I'm 2 miles away and I hit it with a hammer. You would hear it through the metal, and then if you picked your head up quick enough, you would hear it again through the air, because sound travels very fast through solid, very fast. It doesn't travel as well through air. So it's not the speed of the sound, but yep.
It would just be the frequency.
The frequency. What does that mean? The frequency.
Like how high or low the
Yeah.
thing is.
It's going to be how high or low the sound is. So I've been playing this basic sound all week, 1,000 hertz. But let me turn the volume up here. Okay, so there's 1,000 hertz. So if I go up a little higher, we'll see if you can still hear it. Let's go up to, let's try like around 5,000. But I don't want to play 2 different sounds. I want to keep the same sound out of both speakers. So it's up around 5,000 hertz. So it's higher pitch, but was there anybody that couldn't hear it?
I think we need a little higher.
We'll go a little higher. You can see it's starting to compress so much, you're not even going to be able to see a picture pretty soon. So if we go up around 10,000 hertz.
Look at it.
So it's 10,000, but anyone that couldn't hear that one? You can still hear it? Let's go up.
Can you hear these?
I can. So we'll go up around 14, a little over 14,000. That's 14.1 kilohertz, or 14,100 hertz. So I can still hear that. It's very, very high pitch. If we go up around 17,000, no, I can't hear it. I mean, I hear the speaker like crackling, but I don't hear that high pitch sound anymore. And then if you go up high enough, it doesn't want to. It's scared. All right, if you go up high enough, you'll hear I hear the speaker on, like I hear the sound when the speaker turns on, but I'm not actually hearing the sound like the high pitch. I hear a buzzing and like a clicking.
Yeah, you try.
But that's not the sound.
Yeah, can you take one down?
If you bring it down, you would hear the sound.
Oh.
Oh my god.
You hear it now?
Yeah.
Yes, you hear it.
No, I don't hear it at 16,000. About 15,000.
I mean, it's disturbing.
So it's a very high pitched sound.
It's not a pleasant delay. It bothers me. It doesn't really bother me, but it's not pleasant.
Okay. On the other end, you can go to like a lower. So this is going to be a lower pitch sound. It's pretty low, but it's around 100 hertz. Let's go a little lower.
Oh no.
So about as low as I can with that speaker, which is 45 hertz.
I love that.
Can you like harmonize?
So what's interesting about that sound is there are certain objects in here that vibrate at a certain frequency. It's called resonance. So at 45 hertz, I don't really hear anything vibrating. I hear the sound.
My head.
Yeah, my head.
Maybe your brain is vibrating. If I start to increase the frequency, all of a sudden you'll hear something in the room somewhere else that vibrates at the frequency that I'm playing. So as I go up slowly, you'll hear it. So something's vibrating. And the lights. And what's really weird is when I play 45 hertz, I hear it very loud. When I play 50 hertz, standing right here, I don't even hear it. It must be just the way it like echoes, and it's like all the sound cancels right here. Like I don't even hear that really.
If you move, can you hear somewhere else?
Yeah, it got very loud over here.
Let's not be
That's how, when they get snow on the roof, that's how I get it off. Just gets it all off. So when you get to the lower frequencies, it starts to vibrate different things. And if you've ever seen like somebody singing, sometimes they show like a video like breaking like a wine glass or something. You can do that, but what you have to figure out is the exact frequency that glass vibrates at. So if you have a piece of glass and you just just hit it like that, you'll hear that like that ping, kind of sound. Well, if you have a microphone, it can pick up the frequency and tell you exactly what that frequency is. And then if you play that very loud, then it could break the glass. So singing is kind of hard because you have to hold that exact frequency and it has to be loud enough. Now this is glass, but when I hit it, it doesn't do that like ping kind of sound. Same thing with the windows. Like if I hit them, it's not going to make that sound because the glass is held in on every edge. So it's basically, because it's held in, it can't vibrate. It's stuck. But a glass just on a table, there's nothing holding the glass. The only thing it's touching is the base of the glass. And especially with like a glass that has a thin stem on it, the top part of the glass can vibrate, and that's why you hear the sound. If you hit the base of it when it's on the table, you probably wouldn't hear it because the base is being held solid. So you can resonate different objects and they'll start to vibrate. So you just have to know the right frequencies. All right. So that's horizontal, stretch, and compress. So what they might ask us about this one is, now that you've stretched or compressed it, what is the new period? All right. It starts out as 2 pi. To figure out the new period, this is the formula. Bless you. You use.
Thank you.
Must be the frequencies. Could cause you to sneeze. That's the frequency. If you play 57 hertz, clears your sinuses right out. Probably not.
Let me try it.
So 2 pi over b. That's the formula to calculate the new period. So on the test, you're going to have a couple problems, just like when I said find the amplitude. It's going to say find the period. No graph required at all. Just find the period. So remember, the period is not 2 pi by itself. It's not b by itself. It's when you divide both of them. Right? So b is just the number in front of the x. 2 pi divided by that number, and that's your new period. Okay. So let's try this one. So they always use t for the period. I'm not sure why they use that letter, but that's what they use. It's going to be a fraction. Okay. What goes in the top of the fraction?
2 pi.
2 pi. That never changes. It's always 2 pi. And now what goes in the bottom, this changes. Depends on the problem. So what b goes in the bottom, and what's b in this case? 2. So what that means is the period of this graph is now pi. Is that a shorter period or a longer period than the original? It's shorter. The original period is 2 pi. This one is 1 pi. So that means this graph would cycle twice as fast. Okay. Let's look at this one. Cosine 1/3 x. So we're going to have a fraction. What goes in the top? 2 pi. What goes in the bottom of this one? 1/3. So what do you get if you take 2 pi and divide it by 1/3? Yeah? 6 pi. Right? If you want to divide by a fraction, that's the same as multiplying by the reciprocal. So you can think of it as 2 pi times 3/1. So that's 6 pi. Is that longer or shorter than the original? Much longer. The original is 2 pi. This is 6 pi. It's triple the length. Okay. Let's do this one. Sine of pi x. What would the period be here? Pi is part of it. That's just the denominator, though. What goes in the top? 2 pi. So now, same question I just asked. What's the period? 2. So if we were to graph this one, this would actually be a very nice graph. Your x-axis labels would be very nice because the pi's canceled out. Arithmetic would be very easy here. All right, and what about this one? There's a lot of stuff happening, but just focus on the one number that's important for us and what to do with that number. Put it over, under 2 pi. That's your period. There's a vertical shift 2 units up. There's also an amplitude change. Those have nothing to do with the period. Any questions on that? Okay, you'll have 2 questions just like that. If this was multiple choice, I would probably give you 3 as a choice. Don't pick 3. 3 is just what goes in the bottom. It's 2 pi over 3. All right, the last thing we got to look at is how do we graph it. So we've got our original table. We've got 5 points in the table. We're stretching and compressing horizontally. What values is that going to change? X's or Y's? It's going to change all the X's. So this time, the Y's stay the same. So copy those down from the original table. Now the X's are all going to change. The way you find your new X's is just take the old X's and divide by B. Now, if B is a fraction, then we're going to end up dividing a fraction by a fraction. We want to remember that if you divide by a fraction, that's the same as doing what? By the reciprocal. So if B is an integer, a number that's not a fraction, then we'll just divide by it. But if B is a fraction, we don't want to have to deal with fractions over fractions. So we're going to end up multiplying by the reciprocal of B. So you'll see that as we go. Okay, so let's look at this one. Sine of 1/2 x. This would take your graph and stretch it. It would stretch it out. Remember, small numbers actually make the graph bigger. Inside is always backwards. Okay, so I know it's a period change because why? How do I know? Why isn't this like a phase shift or an amplitude change? Why is it a period change? 2 things. You're multiplying inside. Multiply inside. So we just said x's are going to change, y's stay the same. Connor, what are my y values for sine?
0, 1, 0, -1, 0.
Yep. And now my x's are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now we're going to divide all of those by 1/2. That's what the directions said to do. But 1/2 is a fraction. Dividing by 1/2 is the same as doing what? Multiplying by 2. So that's how I'm going to think of this one. Double everything. Start with 0. If you double 0, what do you get?
0.
0. How about pi over 2 doubled?
Pi.
Pi. How about, bless you, when you double pi, what do you get? 2 pi. How about when you double 3 pi over 2? 3 pi. And when you double 2 pi? 4 pi. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. Are those all equally spaced?
Yeah.
Yep. They're equally spaced if there's a pattern. Same pattern. Because they're equally spaced, you can use those to label your graph. They're always equally spaced if you've done it right. So this is 0, pi, 2 pi, 3 pi, 4 pi. And my y-axis, 0 in the middle, and then 1 to -1. Okay, now when I do my graph, this graph should look stretched out. To me, it looks exactly the same as every graph we've done for sine all week. It's scaled, right? The normal sine function would look kind of like this. I can't. I'm trying to just stretch it on one direction, and it won't let me. Let's try doing this. See if I can do it now. All right, now it's letting me. So the normal one, if you were doing it on this graph, would look something like that. It's a little off, but you get the idea. It would be between 0 and 2 pi. This one has been stretched out. All right, let's try this one. Y equals cosine 2x. Okay, what column stays the same? The y's. 1, 0, -1, 0, 1. Now, what do I do to all my x's? Divide them by 2, which is the same as what? Multiplying them by what? 1/2, yeah. So basically just take half of all of these. Well, half of 0 is still 0. If you haven't done a phase shift, the first one is always 0. Because 0 times anything is 0. If you shift it, then the first one might not be 0. We'll see that tomorrow. What's half of pi over 2?
Pi over 4.
Pi over 4. What's half? Well, half of pi is just half of pi. Pi over 2. What's half of 3 pi over 2?
3 pi over 4.
Yeah, just times 1 over 2 times 1/2. So 3 pi over 4. And half of 2 pi? Pi. Now, if you look, it's like, oh, those don't look like a nice pattern. It's because they don't have the same denominator. That's 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. We just reduce all those as much as we can. So they are all nicely spaced, so use those as your labels. 0 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, but I reduced it as I went. It's going to look just like the same cosines we've been doing all week. 1, 0, -1, 0, 1. That wasn't that good. Wrong spot. So up until now, you've had to make sure you label your axes. If you don't label them, I'm going to assume you're going to go by ones. 0, 1, 2, 3, 4. And these numbers are not nice numbers. Okay, that's like 1.57, 3.1. We don't want to go by that. So always label them using the labels in your X column. Unless you're going by ones. So technically, if you didn't label your y-axis here, I would still mark that correct, because I went by ones. Let's look at this one. So cosine pi over 3x. Now, when you have pi in front of the x, you might think, wow, that one looks like it's going to be pretty bad. Usually these ones work out the nicest. So we're going to get a very nice coordinate. So the y's we just did. Now here's my x's. They all have pi in them. But the number in front of x also has a pi in it. So we're going to see something that happens. So I could divide all these by pi over 3, or multiply by what? 3 over pi. Well, the first one is 0. Let's look at the second one. Pi over 2 times 3 over pi. What happens there? Pi's cancel. And all you're left with is 1.5. Now, what's the gap between 0 and 1.5? So the gap should be 1.5 each time. It should be 3, 4.5, 6. Let's just do 1, 1. So pi times 3 over pi. The pi's cancel, and you get 3. So the next one is 4.5, and the next one is 6. The next one, if you kept going, would be 7.5, and then 9, 10.5, 12. There you go. So now we've got nice values in the x column, nice values in the y column. If you want to go by ones, you don't have to label anything. Okay? Have I got enough room? No, I think I need one more. So in this one, I'm just going to go by ones. So 0, 1 is right there. 1.5, 0. I mean, it's in between the lines, but it's only a half. It's not that hard to find it. 3, negative 1. So, let's see, 3, negative 1. 4.5, 0. So 1, 2, 3, 4.5, 0. I like to still put the labels. For me, it's just easier to see it. And then 6, 1. 6, up 1. And then make your graph. So any questions on the stretches? Okay, so tonight's homework, 8 questions, very similar to last night. Again, it's on a worksheet, so you don't have to write it down. Make sure you show the table, just like I did in class. And tomorrow we'll finish up with sine and cosine.